All right, welcome everybody. So I've gotten a couple of questions on homework 7. It seems like people are getting an early start on that, which is good. It's due before class on Tuesday, and we're going to cover a couple of example problems today that will address the rotational flow, and then you'll have everything you need to solve that problem. I sent out a hint related to that assignment, just reminding you that a differential manometer, which is connected at two different points, that the change in elevation in the two piezometers, the deflection, delta H, is a result of the change in piezometric pressure. So if it's horizontally oriented pipe, then it's just the change in pressure, since the two Z values are the same. But when it's vertically oriented, there's a difference in Z values, and that differential pressure measurement that you get from attaching two piezometers, it takes the elevation into account. So my suggestion is go through that process of defining what is piezometric pressure, P sub Z. Remember, P sub Z is pressure plus gamma times Z. And then the change would be pressure plus gamma Z at one location minus pressure plus gamma Z at the other location. So if you kind of go through the substitutions between that and Bernoulli's equation, I hope that you'll algebraically see that you have all the information you need in order to find the new velocity. All right, so today we've moved on from talking about local acceleration and how we used Euler's equation to predict changes in pressure and liquid elevation due to local acceleration. Remember that if you have an enclosed tank so that the water level can't change, then it's just the pressure that is affected by a local acceleration. But if you have a free surface of water where it's in contact with the atmosphere, when you accelerate an element of water, then that free surface will tilt related to the direction that you're accelerating in. And for instance, if we are accelerating some water, if we have a tank of water and I accelerate it in the x direction, so to the right, positively, then what's going to happen is that the liquid level will rise on the left and decrease on the right. So the rule of thumb that we've used so far is that the pressure or the liquid level increases in the opposite direction of acceleration. So if we're accelerating to the right, then the liquid level is deeper on the left. And the same is true if it's an enclosed tank. So think about the examples we've done with Euler's equation where we had location maybe A and location C. And if we're accelerating it to the right, we know that the pressure would be increased in the opposite direction. Now there's also an elevation difference here that we'd need to account for, but the pressure at A would be higher than it otherwise would be if the tank wasn't accelerating relative to C. So the rule with Euler's equation was that the pressure increases in the opposite direction of the acceleration. And that same rule of thumb will hold today. Let's watch a little video that just kind of defines and helps you to visualize the ideas behind centripetal acceleration. All right, so this is from YouTube. All right, so just pausing on this for a moment. Notice that the acceleration is towards the center. And sometimes that's a little bit counterintuitive to people because they feel the force on their finger. Like if you were actually doing the spinning, if you were the person who's spinning the can and causing that rotation, then you'd sense that the force that you're experiencing is that the can is kind of pulling your hand outward. And so you maybe would be tempted to think, well, the acceleration is outward. But if you think about it for a moment, the acceleration has to be inward towards the central axis, otherwise the can wouldn't continue its circular path. Like if you immediately cease the acceleration, as it's going to illustrate in just a moment, it will go in a straight path. And so then if you don't cease the acceleration, that's what allows the can to have a curved path of motion. Why it's traveling in a circle is because the acceleration is inward. So just think that acceleration is changing the velocity, and it may not change the magnitude of the velocity. You know, it can be spinning at the same speed, but what the acceleration is doing is it's changing the velocity's direction. At every moment, this can is, you know, from our perspective, it's turning left, you know, because it's rotating. I guess if we were going to say it's rotating counterclockwise, it's always making that left turn because of the acceleration that's applied. It may be a little bit unnecessarily complicated when he starts talking about the force inside the can. I'm not sure why he put a fly, or I guess that's maybe a yellow jacket in the can. But so hopefully that visualization gives you an idea of the where the centripetal acceleration, how it arises. And let me show you one more little video for now. This is a video that's showing a tank of water that's being spun. Let me just pause this. Is a formula that will allow us to describe the shape of this liquid curvature. Now this is open to the atmosphere, and so the water can slosh around and change its elevation. If you look at the beginning, you know, there's only, you know, a little bit of liquid at the bottom. They could have put a glass plate on top of that liquid, and so if they did that so that the liquid surface couldn't change, the pressures would be adjusting, even though the liquid level isn't. But when you have it open to the atmosphere, then the liquid level is changing, and so of course the pressure is zero, where the air is in contact with the water, but then as you go downward, the pressure is increasing just according to the hydrostatic equation, because in the vertical direction there's no special acceleration just besides the effect of gravity. All of the acceleration when this is being spun, the additional acceleration beyond gravity, is inward towards the center. So the equation that we're going to use today, in some ways it has similarities to Euler's equation, because, you know, in Euler's equation you didn't have to separately account for the effect of gravity. That was already built into Euler's equation. And then the same is true in the equation that we'll use for rotational flow. The hydrostatic effect of pressure increasing as you go down through a fluid, that equation includes the hydrostatic effect as well as any additional change in pressure that may be caused by a centripetal acceleration. So if we want to define some terms here, then we can calculate the velocity of a particle that's traveling in a circle by multiplying the radius of curvature from the center of the point at which it's rotating about out to where the particle is. So the radius multiplied by the rotational rate in radians per second. Now, this angular velocity in radians per second, the thing to keep in mind is that in the SI unit system, radians is unitless. In SI, all units can be derived from 3 base units: time, length, and mass. And radians doesn't have any of those. And so when we put it into the equations, it's really just the seconds that that applies. For instance, we know that accelerations have units of meters per second. And so consider now this formula below, which is for to calculate the radial acceleration. So meters per second on the left-hand side. On the right-hand side, where does that units of meters per second comes from? Well, it's the tangential velocity squared divided by the radius. Now that's obviously meters per second squared, because it's meters squared per second squared in the numerator, and then you divide by the radius, and that cancels out one of the meters. But then over here, if we solve for it in terms of the angular velocity squared, it's just inverse seconds that are being squared. And so it's meters per second squared. So that's sometimes something that gives students a little bit of confusion, this idea of ignore the radians aspect of the units in angular velocity. But that's because radians are unitless in SI units. So from this, if you know the speed of a particle as it rotates, you can calculate its radial acceleration. And sometimes things that are rotating will be described in terms of how many revolutions per minute they're experiencing, RPM. And so if you are told how quickly something is spinning in terms of revolutions per minute, and you need to know its radians per second, then the conversion process for that is simply to multiply by 2 pi, because that's how many radians there are in a revolution, and then divide by 60, because that's how many seconds there are in a minute. So RPMs times 2 pi divided by 60 will give you radians per second. All right, so rotational flow applies to a variety of situations in nature, like a fluid vortex. A tornado is spinning radially, and you can kind of simulate and model this behavior. You can build kind of a demonstration scale water vortex. All right, now these tubes that have a U shape are sometimes used to introduce and get some practice using the equations because it's easy to visualize what the water is doing in reaction to the centripetal acceleration. So the way to interpret this picture is it's being rotated about the left leg. And so right now this leg is on the right side, but because it's spinning, this leg, which is on the right now, will be on the other side in a moment. So if you looked at it from above, this stays in the same spot, but the other leg is sweeping about. And the deflection in the two water surfaces you can see is 25 centimeters. And the radial distance between the left leg and the right leg is important, because the further apart they are, the greater the magnitude of the acceleration that's being experienced in the right leg over here. So in problems like this, where we're trying to solve for what is the rate of rotation, or sometimes you've been given the rate of rotation and you want to find how far is the deflection, the problem-solving process is to start at a location where you know something. And as we've done before in other problems, it typically makes sense to start at the surface, the interface between a liquid and a gas, because you know that the pressure here where the air is touching the water, the pressure is 0. So here's the equation, and sometimes people mistakenly think of it as related to the Bernoulli's equation simply because the first two terms of this equation are the same as the Bernoulli's equation, but of course the third term here isn't the typical velocity head term that we use in the Bernoulli's equation, but rather it's the place where we account for the effect of the rotation of the fluid. So you'll notice that all of these terms have the same units that we've added for them before, like pressure has units of pascals, elevation has units of meters. When we substitute the rotational rate into the equation, it needs to be radians per second, and then the distance from the axis of rotation should be in meters. And that's missing from the slide. Let me just add that. Meters. Okay. So it's not the Bernoulli's equation. Now, what we're going to do for this image is try and find out what is the rotational rate that's being experienced. We will use location 1 is here where it's spinning about. So that's location 1. Location 2 will be over on the right leg. Let me sketch this on the board. And then let's go through the process of making some substitutions into that equation. Oops, that's the wrong slide. All right, so back to this one. So here's our U-shaped tube, and the water level rises on the right because that's the opposite direction of acceleration. If it's rotating about the left leg, then the acceleration is inward. Okay? So we're going to say here's location 1 on the left, location 2 is on the right. The known deflection is 25 centimeters. And we want to find out how quickly is it spinning in terms of radians per second. All right, so let's think about what we know and what we don't know at location 1 and location 2, like for substituting into this formula. We know that the pressure at 1 is 0 because it's in contact with the air. So it's atmospheric pressure, and we're going to use the atmospheric pressure as our gauge datum. So pressure at 1 is 0, pressure at 2 is also 0. And what about elevation? Well, let's say that Z1 is 0 and Z2 is 0.25 meters because it's 25 centimeters above the left side. Now, we could also measure our elevations using like the bottom of the tube as the reference point. So if I knew how far it was from the liquid level to the bottom of the tube, I could have used the bottom of the tube as my datum as long as we use that same reference point for 1 and 2. Or I could have said, let location 2 be Z equals 0, and then that would mean Z1 is negative 0.25 since it's below. But I think it just is most straightforward if we say Z1 is 0 and Z2 is 0.25. Okay, R. The radius is measuring how far is the point from the axis that it's being rotated about. And since it's being rotated about the left leg, then that means that R1 is 0. And R2 is 0.10 meters. Okay, now if we write this equation here, so it's the pressure head plus the elevation minus omega squared radius 1 squared divided by 2g is equal to the pressure head at 2 plus the elevation head at 2 minus omega squared R2 squared divided by 2g. Sometimes people get in the habit of writing subscripts, you know, because it's P1, Z1, R1. Omega doesn't have a subscript. There's just a single rotational rate. There's not a separate rotational rate for the right side and the left side. It's all rotating at the same rate. So note that. Also, make note of the minus sign. It's not a plus, it's a minus. And so that's another frequent error. Okay, so P1 is 0. Let's cancel out the pressure head term. Z1 is 0. We cancel out the elevation head term. P2 is 0. We cancel out that. Since R1 is 0, then it cancels out this term. So all of the terms on the left-hand side cancel out. So what that leaves us with is Z2 is equal to omega squared R2 squared divided by 2g. All right, so you can rearrange that algebraically and solve for omega. Let me give you a moment to do that while I pull open the solution and put it up on the screen. Okay, 22.15 radians per second. That's what it would take to cause that deflection. Now think about it, if things were different. If the right leg was further away, then it wouldn't need to go so fast. The fluid properties, it's interesting. No, the fluid properties are all canceled out. Right? Yeah. Here, where we're solving for omega, the unit weight of the fluid is no longer in the equation. All right, so the next part of this, part B, find the radial acceleration experienced in the right leg. So we know the radius is 10 centimeters. We know the rotational rate is 22.15 radians per second. And so the acceleration experienced in the right leg is going to be 22.15 squared multiplied by the radius. So it's 49.05 meters per second squared. And then finally, if we wanted to calculate the tangential velocity, so you can think of that as like, what's the actual speed? If you cut the rope on the can, what would be the speed of the object if it continues forward? What is the speed of that outside leg as it sweeps through space? So we multiply the radius by the rotational rate in radians per second. It's going 2.215 meters per second. All right. Now this one was open to the atmosphere, and so the liquid level was able to react as it began to rotate and experience the acceleration. In the case of this enclosed tube, the liquid level is all the way up to the top of the container. So it's full of a liquid. It's full of oil with a given specific gravity. So that's going to affect the unit weight that we use. And we have 2 points. There's this point L, which is in the base leg, and then point M, which is 12.5 centimeters above location L. And you can see that the radius of each side is defined. It's not rotating about one of the legs. It's rotating somewhere in the midpoint. So what we can do is apply this equation where you know the pressure at L, that's given, and we're trying to determine the pressure at M, that's the unknown. In this equation, it doesn't matter if one is on the left or if one is on the right. In Euler's equation, we had to be pretty careful about which was location 1 and which is location 2, but here for the rotational flow, we don't. So I'm going to pause for a second and give you a moment to calculate the pressure at M. And so you're going to have to substitute in the known pressure, the elevations, the radius, all the details that you're given. And here you can see it's 25 RPM. RPM is revolutions per minute, so you need to convert that to radians per second. All right, so there's the left side, point L, there's the right side, point M. We're making all these substitutions for the pressure, elevation, radius. Calculate the unit weight based on the specific gravity that's known. Convert the revolutions per minute into radians per second. And then here's the formula we're going to be substituting into. What I did was I just rearranged it to solve in terms of the pressure at M. Rather than making the substitutions first, I did the algebra first. Okay, and then here's all the numerical substitutions. And so the mistakes that's easy to make is it's easy to forget to square the omega and the radius. That's easy to overlook. And then, of course, I threw you a curveball here because I described the pressure in terms of kPa. So there's a units issue there. If you're going to be using the unit weight of 8338, you can't write 2.7 for the pressure. You have to expand that out to be 2750 newtons per meter squared. So converting from kilo to just the normal pascals. So then as I always do, just kind of calculated these intermediate quantities, and the advantage of doing this is you can kind of just see where the pressure is coming from. Like, where is this pressure at M derived? So the majority of the pressure at M is from this term that was the pressure at L. And if there's pressure at L, there's going to be pressure at M. And then all these other things subtract away from it. So for instance, the fact that it's higher in elevation, the 0.125 meters, that's reducing the pressure. So here the elevation difference is accounted for. And then the fact that, let's see, which one is further away from this axis of rotation? So L is further away than M from the axis of rotation. So that means that the pressure at M won't be as high as it will at L, simply because it's closer to the axis of rotation. So then the net effect of that is this minus 0.05 is greater than the 0.006. So all in all, the pressure that you calculate should be 1339 newtons per meter squared. That will be the pressure at location M. Any questions about the steps you went through to calculate this pressure? All right. Let's do one more example. And this one has the potential to get relatively complicated. There's two parts to this example. What we're looking at right now is the before. Before it started spinning, the liquid levels were the same on each side. But then it began to spin, and it's going to achieve some different water elevations than we see right now. So once it's spinning at 8 radians per second, one of the sides is going to have the liquid level go down, and one of the sides is going to have the liquid level go up. Can you tell just by looking what side is the water level going to decrease and what side will it increase?
Increase on the right.
Increase on the right. That's correct. How come? Why will it increase on the right and go down on the left?
There's more distance between the right side and the center of rotation.
That's right. So it's more distance, so the higher radius means that there's more acceleration being experienced on this right leg than on the left. And of course, when I call it the right leg, it's on the right now. It's going to be spinning, and so it'll alternate which side it's on from our perspective, but it will continue to be the case that one of the legs has a radius of 36 centimeters and the other has a radius of 18. And so the leg that has the radius of 36 centimeters, the liquid level is going to go up. Now here's a really important idea. They appear to be, by inspection, the same diameter on the left and the right. The tubes. So this is a circular tube that we're taking a cross-sectional view of. And so let's assume that it's the same diameter all the way. If it goes down 1 centimeter on the left because of the effect we've just talked about, how much is it going to go up on the right? 1 centimeter. So what we could say is that the z on the left is related to the z on the right, because for every decrease on the left, it will have a corresponding increase on the right. And so the way I'm going to write that is like this. You know, we're going to have an equation with two unknowns to find the equilibrium height. You know, if you just kind of think ahead, like where is this going? It's saying find the equilibrium water elevations. You're going to be solving for Z1 and Z2. The pressure, we're going to use 1 as, like when it starts to spin, the water level is down on the left and up on the right. Okay, so here will be location 1, here will be location 2. All right, so we know R1 and R2, we're good there. We know P1 and P2, we're good there. Omega is given, and it's even in radians per second, so no adjustment necessary. But in the equation that we're going to have remaining, Z1 and Z2 are both unknown. So it's kind of like we've got two unknowns, but the other equation we can use is Z1 plus Z2 equals 0.36 meters. So what I'm saying is let's measure from the bottom here. And the total elevation is the distance on the left and the distance on the right. So this equation, Z1 plus Z2 equals 0.36, is what we can use in order to find Z1 in terms of Z2. All right, so I'm going to pause for a second here and find out the equilibrium water elevations, like how high above the bottom base will the liquid level be on the left versus on the right if it's rotating at 8 radians per second.
And the liquid is water?
The liquid is water, yes. Okay, so first we're going to see at 8 radians per second what's happening. All right, so here's our system going 8 radians per second. I already sketched on the whiteboard the fact that the water level will rise at 2 and decrease at 1. And we want to know essentially how much does it go up on one side and down on the other. And so the continuity term here is just that the two heights collectively will always equal 0.36 unless the liquid level starts going into this bottom base, like if it's accelerating really fast. But for now, until the liquid level gets down in this bottom base, then the sum of the two elevations are 0.36. All right, so if we know that the pressure at 1 is 0 and the pressure at 2 is 0, you can see that I've canceled out the pressure head terms from that rotational equation. And what remains on the left-hand side is the difference in elevations. And for Z1, I'm substituting in 0.36 minus Z2. So now this equation otherwise would have two unknowns. Z1 is an unknown and Z2 is an unknown, where we know omega, we know R1, we know R2. But by making this substitution, now there's just a single unknown in the equation. And we can rearrange that in terms of Z2. So here you can see if we had 2 Z2s, that's why I'm dividing by -2 after grouping everything else to the other side of the equation. And so here are the substitutions that I've done, and the elevation on the right side, Z2, should be 0.3385 meters. So that means Z1 will be 0.36 minus this. So Z1 would be 0.0215 meters. Now this only holds up and is true as long as the liquid level isn't down into the bottom base. But if we start spinning faster and faster, that's exactly what's going to happen. Here I pose the question, what happens if you increase the rotational speed to 14 radians per second? So before you do any calculations, just think qualitatively that eventually all of the water that's here on the left will be in the right side. And then what happens at that point when you're spinning really fast is that, let me just draw this. At that point, the liquid level is over here somewhere and it's getting really high. So here would be location 1 and here's location 2. So think about what equation could we use to describe the elevation of location 2 when the liquid level gets over into that other side. Now, the way that you know that you need to switch over and transition is we could just substitute in this other rotational rate, 14 radians per second. What if I did that in here? So I've rearranged the equation for Z2. What if I just switch, instead of 8, if I put 14? So if I do that the rotational rate is 14, then I get Z2 is 0.6655, which means that you'd have to have a negative number for Z1. And that's not possible. The water level won't go below the bottom of the base. And so that tells me that I've got to that threshold point where the water is no longer in the left side, and now it's starting to retreat in the bottom base tube. So if you just substitute it in, it's not possible for the water level to go below 0. So that means it's this equation, or this situation where 1 is somewhere on the left and 2 is rising even higher. So it's going to be at least 0.36 because all of the water that was on the left side is now on the right. So that's where the 0.36 comes from. And now what we're doing is we're relating the elevation at 2 in terms of where the radius is at 1. And so this becomes a little more tricky because in the past we were able to just know exactly what the radius was. That was a given. R1 and R2 was known. But now the unknown is what's the elevation at 2 and also what's the radius at 1, because depending on how quickly it's spinning is going to have an effect on how far from this axis point location 1 is. And if we're spinning really, really fast, it could even be that the liquid level is on this side of it. You know, the liquid is over here, in which case you'd use a negative value for the radius if it was all the way to the right. I've lost a cap. I'll find it later. I just wanted to show you the calculations in this case. So the idea is just that for every centimeter that the radius continues to retreat, then the elevation on the right increases by 1 centimeter. So if you wanted to find out what's happening when the radius is when the rotational rate is 14 radians per second, here at 1 there's no elevation because we're using the bottom as our elevation datum. There's no pressure, but we're trying to find out what is R1. So that term still is there. And at 2, there's no pressure head. The elevation is unknown, but we do know the radius. So the term that we developed here, Z2, is 0.36 plus 0.18 minus the radius. And the reason why it's 0.18 minus the radius is there was 18 centimeters of liquid there. So whatever the radius is, the amount of liquid that is rising at location 2 is dependent on how much the radius is retreated from the center axis of rotation. So like, for example, if R1 is 9 centimeters, how much water is there over on the right? It's going to be 36 plus 9 because it's retreated 9 centimeters from the 18 that it used to be. All right, so when you set this up, you're going to get that there's actually roots of the equation because you're going to have a radius is an unknown, and so you're squaring it, and then you're going to have an unknown radius term that isn't squared. So there will be a negative root and a positive root, and the negative root means that the water has retreated into the right side. So that's this case that I'm illustrating where if radius is positive, one of the roots says that the water would have to be at 0.32 meters. But the maximum radius is 18 centimeters. So that's why this positive root doesn't make sense, is that the furthest away it could be is 18 centimeters. So then the negative root, paradoxically, is the root that makes physical sense, because we do have a distance of 36 centimeters from this axis of rotation. So what this is saying is you're going to the right 22 centimeters. So it's 22 centimeters from here to where the water sets up, and then all of the rest of the water has shifted into the to the right side. So it's gone up to an elevation of 0.769 meters. So it's the 0.36 plus the 0.18. So it's all of the water. So how much water is there in the right leg? It's the 18 that was there to begin with, plus the 18 on the left, and all of this water has shifted over to the right side, plus the additional 22.9 centimeters. So there's a lot of water over in this right leg if we start the rotational rate up to 14 radians per second. So the tricky thing is just finding an equation that relates elevation and radius. Any questions about this example before we break for today? Where's the cap? There it is. We have a minute, so let's just pull open the homework assignment and make sure that we've covered all of the problems that you've got to work on by Tuesday. Okay, Bernoulli's equation, pitot tubes, and rotational flow. So this is an orifice equation where, rather than just the normal orifice equation of velocity is square root of 2gh, here you have to actually use the full Bernoulli equation because it's not open to the atmosphere. It's pressurized inside of the tank. So your pressure at 1 at the surface is going to be some positive given value rather than 0. We talked a bit about problem 2, and I gave you a hint related to that one. We've got another Bernoulli equation here. All right, problem 4. An important thing I want to point out is that it's both the effect of stagnation. Remember, stagnation is where the velocity gets translated into some additional pressure and it pushes the water up. So part of the reason the water is getting pushed up is because of stagnation, but then it's also a surface tension effect. So I've told you the diameter of the tube, and you may remember some problems we did back in chapter 2 where we were talking about how for a small diameter capillary tube, the water gets drawn up because of the liquid's attraction to the glass. And so it's trying to maximize contact with that silicon dioxide that the glass is made out of. So you need to calculate what distance of the rise is due to the capillary effect for this given tube diameter, and then what distance is because of the stagnation, and combine them together. All right, we've done an example like this on the board in class, although I don't think we used nacho cheese sauce as the manometer fluid before. Pitot tube problem. All right, and then here's a couple of these irrotational flow problems where you're spinning about a base leg. In this one, you want to find the equilibrium elevation, so similar to what we've just done. And then here's one where we're asking you to find for the rotational rate that will cause this deflection. And notice it's asking for the rotational rate in revolutions per minute. So when you solve for it in radians per second, then you'll have to convert to rotations per minute. And then this one, it's open on one side but enclosed on the other. All right. Well, that's all I've got for you today. This assignment's due on Tuesday, and I'll see you then.